Hello everyone. First, let me thank the organizer for giving me a chance to present the work which we are doing at ICS Kolkata. I am Dr. Praveen Kumar, and today I am going to discuss spin manipulation and basal plane activation of 2D material for photoelectrochemical hydrogen generation. So before I go into the technical part, let me tell you a brief about the work which we are doing at ICS Kolkata. So we work on semiconductor nanostructure, especially for nitride, oxides and silicon. Then we try to understand the various fundamental issues on 2D material, especially for chalcogenide and MXenes. And we are also working on quasi 2D material. And once you have these very wide range of material, then we try to understand their heterostructure, and especially we try to understand their electron transport as far as their momentum and spin is concerned. And once you make the heterostructures, you can change the various properties, and you can make devices like a broadband and cell power photodetector. And we are trying to address the energy density issue in supercapacitor. We are also working very rigorously on photoelectrochemical and electrochemical water splitting and CO2 reduction. And just to understand more in deep the mechanism behind the electron transport and with the momentum and spin, we try to understand them using DFT. So this is what we do at ICS, and what I am going to talk today is the work, a part of the work which we do for the photoelectrochemical water splitting. And especially if I talk about the photoelectrochemical water splitting, like it has a anode and cathode, and whatever anode is active to the light, it is photoanode or photocathode. So basic idea is just to have this material innovative, so that you can excite this electron and hole, you can separate and also do transport. So this is how you have to do it. You need a material where you can have a highly efficient separation and also highly efficient transport. So a lot of materials has been reported, starting from the TiO2 to nitride, and we are also working in several materials. But I'll discuss today related to the 2D material, which the work which we are doing. So if I tell you about the 2D materials, there are more than 140 2D materials, but there are a lot of issues as far as fundamental is concerned. Some of the issues which we can address, like fragile and affordable synthesis of these 2D materials, and electronic conductivity, because if I see here, this chalcogenide has a very low mobility. So that is where when you mix it with this MXenes, we could able to address this electronic conductivity. We are also worked on the critical bend alignment, and also the new topic which we have started at ICS, the spin of the electron, which has been ignored till now. So as far as the fissile synthesis is concerned, we have recently developed two processes at the room temperature chemical processes, by which you can get this 2D material in a layered exfoliation high quality, and you can see the comparison between the industrially available and the method which we have made it. So we have filed the 2 patents, and we have also addressed a very recent issue related to the heterostructures. So to get the efficient charge transport, we have heterostructures MOS2 with the gallium nitride to get a very efficient photocathode. But what I am going to discuss today in detail, how we can activate the basal plane of MOS2, and how we can utilize the spin in JNCASR 2D material. So coming to the first part, if I say that MOS2 has been theoretically predicted as alternative of platinum, but because of the less active of the basal plane, only the edge side and corner side of MOS2 is active, the efficiency of that particular material is not as predicted by theoretically. So people are trying to modify it by platinum, palladium, but that is not the solution overall when you are talking about the commercial scale. So then the defect engineering comes into the picture. But once you do the defect engineering, it is very harmful for the recombination in the PEC. So that is not the solution for PEC. And the other solution has been projected by using the 1T phase, which is metallic phase. So once you use the 1T phase, then it becomes metallic, and it's also not a solution for photoelectrochemistry. Heterostructuring can be solution, but it is mostly reported in theory. So if I summarize, the more or less the work has been reported for only the valence band electrochemistry, but once you excite this electron to the conduction band, there is no report how to activate the basal plane. So we have walked into that. So what we have done, we have made the heterostructures using the MOS2 and MOSE2. So in one experiment we have taken MOS2 on top, in another experiment we have taken MOSE2 on top. So this first we have addressed the material science issue, so we have characterized them. So we have taken the silicon to silicon nanowire just to increase the surface area, active area, and after characterization we could able to confirm the growth not only by morphology but also from the structural and optical properties. and this you can see the complete device where you can see the silicon phonon, MOS2 and MOSE2. So after confirmation of the phonon, then we try to understand their electron transport, and when you understand this valence band and core level spectroscopy from XPS, it says that red shift in selenium and blue shift in this sulfur, and it tells you that the electron transport is happening from MOSE2 to MOS2, and that same has been later probed by the valence band spectroscopy. And we have also done the mode Schottky measurements, and so once we take this MOS2 and MOSE2 heterostructure for photoelectrochemistry, the heterostructure which is having MOS2 on top is giving the better performance, and then we try to understand why this is giving the better performance. So it is giving the lower charge resistance and higher hydrogen generation. Then we try to understand using DFT. So of course it's an indirect band gap transfer, and when you do the projected density of states, it says that the valence band is totally dominated by the MOSE2, and the conduction band is totally dominated by the MOS2. That's a similar way which we got it from the XPS. And once you do the electron density transfer, electron density difference and localization function, it tells you that complete basal plane is activated once you have these heterostructures. And then we try to understand their band structure. So once MOS2 is on top, it shows the type second band alignment. That's what it is giving the better performance, and also your whole active basal plane is active. So that is the reason to have this high activity for these structures. Then after we try to understand the asymmetric 2D material, this has been first invented in 2017 by University of California, and because now the symmetry is broken, that's what they have a strong spin orbit coupling. So once they have a spin orbit coupling, their spin degeneracy is broken, so you have different states for up spin and down spin. So this is basically called the Raspa sprinting. So your some transition becomes forward, and under the magnetic field you can manipulate the spin now. So you can have a Raspa spinning in the valence band, and the conduction band you can have a Zeeman splitting. So once you use this kind of system like MOSSC, they don't have a magnetic element, but still due to the Raspa splitting, they behave a spin manipulation under the magnetic field. So we first have addressed the issue of the synthesis of MOSSC. So we filed a recently patent to synthesize MOSSC in facile base Janus MOSSC, and then we do the photoelectrochemistry experiment. This is the band structures. It shows the Raspa type of splitting in MOSSC, and once you do the the splitting experiment as a cathode, you can see the 1.5 fold increment under the magnetic field. It's 0.4 Tesla, very less magnetic field. Then we try to understand what is happening, because MOSSC doesn't have any magnetic element, but still under the magnetic field it shows the increment. So it shows the lower charge resistance under the magnetic field, and also everything increases overall the performance. So we have done other part of physical property, magnetic measurements, MCD experiment. Though due to limited time I am not presenting here, but we try to understand the mechanism. So mechanism is like this: you have a Raspa splitting in your valence band and Zeeman splitting in your conduction band. So what happens once you excite with the photon? Your photon goes, your electron from the valence band goes to the conduction band as a hot electron, and it relaxes with the phonon, and phonon under this relaxation under the magnetic field is a spin dependent. So at the end what you will have, you have a different probability of relaxation in this direction and this direction. So you get asymmetry in the relaxation. So that is where you have a asymmetry in spin electron density. So this diffuses, so it diffuses from a higher to lower density, and this is called the pure spin current. So this is where you have a spin current and the charge current, and this effect is called magnetogyrotropic photogalvanic effect. And due to this effect, you have a efficient charge separation, and the addition of the pure spin current give us this enhancement in this photo current, and also higher activity in the photoelectrochemistry. So this is the first proof of concept which we could able to establish, and I hope I could able to tell you that we could able to activate the basal plane using the heterostructuring, and also the new area which we say that is a spin manipulated electrochemistry using the Janus 2D material has a lot more to do, and I am looking forward for the collaboration, not only for the fundamental but also for industrial research. And I of course acknowledge all my students who is working day and night for these experiments, and also all my funding agencies and collaborators. With that I say thank you very much.